Okay, so implicit differentiation is when you're taking the derivative and instead of having a function just in terms of one variable, and you're finding the derivative of that, you have an equation relating the two variables. But in this case, think of y as still a function of x. So that's why when I do these problems or did these problems with you guys, I think I replace y with f of x. I just think it's easier to remember, oh, y is a function of x. Anyway, even before we get there, notice on the side here I put, you're trying to find dy dx, but remember that's the same notation as y prime and f prime of x. I just want to make note of that because I'm going to use both y prime and f prime of x in this, but they all mean the same thing. Okay, so before I even take the derivative, I'm going to rewrite it so I can use the power rule. Okay, and now before taking the derivative, so I'm not yet taking the derivative, I'm replacing y with f of x, because that's what it is. It's a function of x, and it's just going to be easier for me when I do that to recognize what to do when I take the derivative. And then we'll plug back in at the end that f of x stands for y. Okay, so let's take the derivative of x to the negative 1 using the power rule. So negative x to the negative 2. And then for the second piece of the derivative, bring the negative 1 in front. So it's negative f of x to the negative 2. But then using the chain rule, we have to do the derivative of the inside, which is just going to be written as f prime of x, equals the derivative of any constant is 0. And so remember what the goal is. The goal is to find dy dx, which is the same as finding y prime or f prime of x. So let us isolate f prime, and kind of clean things up. So I've got negative 1 over x squared, and I'm going to bring this whole second term to the other side. So it's going to be positive f of x to the negative 2 times f prime of x. Again, I'm going to clean this up even more. And actually, let's at this stage, before I even clean it up, let's replace f of x and f prime of x with, y's. So it's negative 1 over x squared equals y to the negative 2 times y prime. Remember, the goal is to solve for y prime, which is the same as dy dx. Well, y to the negative 2 is the same as 1 over y squared. So I'm going to write this right side. I've got y prime over y squared. And to isolate y prime, I'm just going to multiply both sides by y squared. So y prime, or your dy dx, which you're trying to solve for, is just negative y squared over x squared. So that's the first one. And since, before I do another with you here, since problem 2 is saying use your answer from 1a above to find the equation of the tangent line to this function at 1, 1, let's just do that. So we're saying, maybe I'll do it a different color. We're saying that the derivative, or dy dx, is negative y squared over x squared. So the slope, remember, of a tangent line is the same thing as the derivative at that point. So it's saying the point is 1, 1. So we're going to plug in 1 for both y and 1 for x. So this slope is just negative 1. And again, the point is 1, 1. So y minus 1 equals negative 1, x minus 1. Not sure, I don't know if you're allowed to leave it in that form. If you're not, you can say y minus 1 equals negative x plus 1, or y equals negative x plus 2. So that's the answer to number 2. Again, it was referring to 1a, so I figure we just did 1a, so why not do that? Okay, let's do another. Let's do B. Again, same idea. For me and my students, I always find it helpful to, again, replace y with f of x. It just kind of reminds you what to do. Okay, so this is back to 1b. This is the original problem, 3x squared. So it's an equation relating x and y, but y, keep in mind, is a function of x. Minus x, y to the 4th equals 23. Okay, so Again, for me, and I feel like students, it's always been helpful, at least when you're starting this, to replace y with f of x. Just to remind you that's what it is, minus x to the fourth, not x to the fourth, sorry. It's just x. Minus x f of x to the fourth equals 23. Okay, so first one, taking the derivative of 3x squares, that's easy, 6x. This one, we've got 2x times f of x. Originally, we had it as y, so you're going to have to do the product rule. So it's going to be the first times the derivative of the second, so times f prime of x, plus the second f of x times the derivative of the first, which is 7. Okay, and then the next one, boo, is a product rule as well. So, but I'm going to put the minus out front because I'm going to have to distribute that after I do the product rule. So the first, which is x, times the derivative of the second, so 4 f of x times f prime of x, plus the second, which is f of x to the fourth, times the derivative of the first, which is 1. Okay, so that was the left side, equals the derivative of 23 is 0. Okay, what a hot mess. All right, so let's just clean things up, and maybe just so we have more room at this point, now that we've done the derivative, you can replace f primes of x's with y primes and f of x's with y. So we've got 6x plus 7x, plus 7x y prime plus 7y minus, let's distribute the negative, minus 4x y prime minus y to the fourth, okay, equals 0. Okay, all right, so now remember the goal to solve for dy dx, or y prime. So get everything with y primes on one side. There's only 2 terms with y primes. And everything else on the other side. So let's bring over the y to the fourth to the right, minus 6x, minus 7y. And how do we isolate y prime? We'll just factor it out. So when I factor it out of those 2 terms, I'm left with 7x minus 4xy. Right side hasn't changed. And then to isolate y prime, we just divide. So y prime is y to the fourth minus 6x minus 7y over 7x minus 4xy. Hooey, these are detailed. Okay. So let's, I'm going to send, there's C and D, but I'm going to send you my work. And then if you need some help with actually going through that, I can, but maybe my work will help too. Okay, let's turn to 3 and let's do a couple for 3. I'm going to do a new sheet here. Okay, so 3 is partial derivatives. And it's interesting, I don't do the same notation, but what this means is you need to find both of these, right? So it means you've got a function or described in terms of both x and y. And the first one, when you've got this f sub x, it means let's find the partial derivative with respect to x, meaning x is a variable, y is a constant. Whereas this one's saying let's find it with respect to y, where y is the variable and x we're treating like a constant. Okay, so let's do this. All right, so for 3a, we've got, oops, didn't want that. Okay, so 3a, we have xy squared plus x squared y plus xy. Okay, so when we're finding the partial derivative where x is the variable, this is the notation, it may be helpful in this case, and maybe I'll write it underneath, to sometimes people think of the thing that's not involving x like a constant or like a coefficient. So sometimes people find it helpful to put the constant piece in front. plus yx. So again, thinking of these pieces just as constants or coefficients, in other words, like as if they were numbers. So when I find the derivative with respect to x, the partial derivative of this equation, I would say, okay, it's just y squared. Again, think of if y squared was like 3x. If y squared was just 3, then the derivative of that would just be 3. So that's why it's just y squared. Okay, let's do it for the second one. So plus 2 comes in front, yx. Again, y, think of it as a number. So if you're struggling, just put in a number there and see what you would do. And the last one, again, y, just a number. So the derivative of that would just be y. Again, if it were 3x, think of what's the derivative of that? Just 3, or in other words, just y. Okay, so that's treating it as if x were the variable and y were constant. Well, let's do it now the other way. And to do this, let's in red again write down maybe, oh, it's actually kind of already written for us, right? It was written this way to begin with, thinking of with the constant and thinking now, here's like a constant. Think of these just as numbers in front. So if I'm doing the derivative with respect to y, it would be 2xy plus x squared plus y. And some people think it's helpful to write like, so another way to think about this, if you let x equal k, then this would be ky squared plus k squared y plus ky. And again, thinking of k as a constant, so when I take the derivative, it would be 2ky plus k squared plus y, and then you plug in back what you define k to be. So 2xy plus x squared plus y. So again, if you want to let k equal that variable that's being treated like a constant, that may help you. Okay, so those were the partial derivatives with respect to x and the partial derivative with respect to y for 3a. Let's do 3b, just to get an idea. And then again, I'll send you my solutions for C, D, and E, which, whoo, those are doozies. Okay, they're just so detailed. B, natural log of xy plus e to the x. Okay, so the first one we're going to do is we're treating x as a variable. So derivative of natural log is 1 over whatever's inside, now times the derivative of the inside. But think of y like just as k. So if I were doing the derivative of kx, it would just be k. So it's going to be times y, and then plus, then the derivative of e to the x. Again, we're doing it with respect to x, so x we're thinking of as a variable, so it would just be e to the x. And simplifying this, I have y over xy plus e to the x, which is 1 over x plus e to the x, because those y's are going to cancel. Okay, so now let's do, and maybe with this one, it may be helpful for me to just do a substitution to make it easier to see. Okay, so let's, again, in this case, we're thinking of x as the constant. So let's just say let k equal x. So think of taking the derivative of ln of ky plus e to the k. Again, k is just a number in this case. All right, so we do 1 over ky times the derivative of that, which would just be k. Again, think of k as just a number here, plus the derivative of e to a number is just 0, because e to a number is just a constant, so plus 0. So this would be just 1 over y. Actually, so we don't even have to go back and plug in what, in this case, we didn't even have to go back and plug in what k was, because the k is canceled. If we did have to plug it in, remember it's just x. Okay, so those are the partial derivatives. Let's do, so again, I'll send you my work so you can see C, D, and E after you try it. But let's do number 4. Same idea, partial derivatives. So First thing here is this function g is in terms of k and l, and it equals k to the third, l to the fourth, plus 2k minus 7l. And the first thing is, this is just like the problems above, except instead of x and y, we've got this k and l. So first you're going to find the derivative, partial derivative with respect to k. So you're going to assume l is a constant. So when I do that, so think of just l as a number. So it'd be 3l to the fourth k squared plus 2, and since L is just a number, the derivative of minus 7 times a number, well, that's just a constant, so the derivative's 0 there. Okay, so now let's do derivative, partial derivative, now with thinking of L as the variable. Okay, so 4 comes in front, k to the third is just a number, L cubed. 2k, remember k is just a number here, so that's going to be 0. And then minus 7l will be minus 7. Okay, so this is just 4k to the third, l to the third, minus 7. So that was number 4. 5 is super similar. It's just trying to trick you with 5 million variables here. So 5 is, you've got this demand function j that's dependent on p, k, l, y, and t. And it's equal to 100 minus 5p plus 2k minus 3l plus 15yt. Okay, and you're finding the derivative with respect to every variable, partial derivative, which means if the other variables we're just going to think of as constants. So when I'm finding the derivative with respect to p, everything else is just a number. So that means that the derivative of all these pieces that don't involve p are 0. So then I'm just looking at negative 5p, and the derivative of that would be negative 5. So easy peasy there. Okay, so, oops, I just did not mean to erase all that. That was 100 minus 5p, 2l, and this was 15. Sorry, I erased that and did not mean to do that. And this was minus 3l. Okay, so now let's do the derivative with respect to k. Anything that doesn't have a k is 0, so the only thing I have to look at is 2k, and the derivative of that is 2. The derivative, next one, is the derivative with respect to l. Again, ignore anything that doesn't have an l. So I'm just looking at minus 3l, and the derivative is minus 3. Last two is the derivative with respect to y. So I'm only looking at the 15yt. A t is a variable, t is a number. So think of negative 15ty. Again, this here is just a number. So the derivative will just be negative 15t, the number in front. And then, oh, not negative, sorry, it's positive. Why in the world I'm doing negative, I don't know. So positive 15t, you don't have to put the positive. And the last one is the partial derivative with respect to t. Again, looking at this same piece here. So think of 15y as just a number. It could be like 155 or something. So, and you just have t to the first, so the derivative is just 15y. Okay, so that's 1 through 5. Woohoo!